Mars is losing its atmosphere, but what if the Sun is slowly stripping it away? Mars is losing its atmosphere, not all at once, not in one catastrophic event, but particle by particle, day after day, material from the red planet is still escaping into space. That raises a question scientists have been asking for decades. How did Mars become the cold, dry world we see today? The evidence tells us that ancient Mars was very different. Billions of years ago, liquid water shaped parts of its surface. Ancient river valleys, lake basins, and minerals formed in the presence of water still preserve that history. For liquid water to remain stable on the surface, Mars needed environmental conditions very different from those of today. Its atmosphere was likely thicker, and its climate was capable of supporting environments that have completely disappeared. Today, Mars is a dry desert with an extremely thin atmosphere. Something changed. One of the most important forces involved came from the Sun. Our star constantly releases a stream of charged particles called the solar wind. Earth is protected by a powerful global magnetic field that helps deflect much of this flow. Mars does not have a comparable global magnetic shield. That leaves its upper atmosphere directly exposed to the changing environment of space. When the solar wind reaches Mars, it interacts with charged particles in the planet's upper atmosphere. Some atmospheric particles can gain enough energy to escape the planet's gravity. Others can be accelerated by electromagnetic forces or knocked away through energetic interactions. Scientists already knew that Mars could lose its atmosphere through several different processes. But in 2026, researchers identified something remarkable. At the boundary between the solar wind and the plasma environment around Mars, enormous wave-like disturbances can form. They are called Kelvin-Helmholtz waves. The basic idea is surprisingly familiar. When wind moves across water, differences in speed can create rolling waves and swirling vortices. In space, something similar can happen when different streams of plasma move past each other. And around Mars, those invisible waves may help carry atmospheric ions away from the planet. This discovery does not explain every part of Mars' atmospheric history, but it reveals another process still happening today. A process that scientists can actually observe. Mars is still losing its atmosphere, and now we are beginning to see one of the ways it happens. To understand why Mars is vulnerable, we have to begin with something the planet no longer has: a powerful global magnetic field. Earth is surrounded by a magnetic field generated deep inside the planet. This field helps redirect much of the solar wind around Earth. It is not a perfect shield, and Earth can still lose particles to space. But the magnetic field creates an important layer of protection between the solar wind and the atmosphere. Mars is different. Today, the red planet does not have a strong global magnetic field. It has localized regions of magnetized crust, remnants of an ancient magnetic environment. But those regions cannot protect the entire planet. So when the solar wind arrives, it can interact much more directly with the upper atmosphere of Mars. The solar wind is not ordinary wind. It is a continuous stream of electrically charged particles, mostly plasma, flowing outward from the Sun. It also carries magnetic fields through space. When this flow reaches Mars, the interaction becomes extremely complex. Electric currents form, magnetic fields bend and compress. Charged particles can be accelerated. Mars creates what scientists call an induced magnetic environment as the solar wind interacts with the planet's ionosphere. But this boundary is not stable. It changes as conditions in the solar wind change. Sometimes atmospheric particles escape gradually. Sometimes solar activity intensifies the process. And sometimes the difference in speed between neighboring regions of plasma creates something even more dramatic: a rolling instability. This is where Kelvin-Helmholtz waves enter the story. Imagine wind moving rapidly across the surface of water. If the difference in speed is large enough, the surface can become unstable. Waves begin to grow. They can curl, roll, and form vortices. A similar physical instability can occur in plasma. Near Mars, the fast solar wind can move past plasma associated with the planet. The difference in velocity can destabilize the boundary between them. But these are not waves made of water. They are structures made of charged particles, and that makes them important for atmospheric escape. When these structures form, they can help organize and transport planetary ions away from Mars. In other words, the boundary around the planet is not always smooth. Under the right conditions, it can begin to roll, and some of the atmosphere can become part of that motion. But proving that these giant plasma waves were truly responsible required something scientists had rarely been able to do before. They needed to observe Mars and the incoming solar wind at the same time. For years, spacecraft orbiting Mars detected unusual structures in the planet's plasma environment. They appeared as localized clouds containing planetary ions moving away from Mars. These clouds could carry substantial amounts of material. That suggested atmospheric escape was not always a smooth and continuous process. Sometimes Mars could lose ions in concentrated bursts, but scientists faced a major problem. Where were these clouds coming from? A spacecraft near Mars could detect an escaping structure, but it was difficult to determine whether that structure had formed near the planet or whether it was connected to a disturbance already present in the solar wind. To answer that question, researchers needed another point of view. That became possible by combining observations from NASA's MAVEN mission and China's Tianwen-1 spacecraft. MAVEN has spent years studying Mars's upper atmosphere and its interaction with the Sun. Tianwen-1 provided measurements of conditions upstream of Mars, helping scientists monitor the solar wind before it reached the planet. This simultaneous perspective was crucial. Researchers could compare what was arriving from the Sun with what was happening near Mars. The result provided direct evidence linking large plasma clouds to Kelvin Helmholtz instability. The observed clouds were not simply random structures. The data indicated that they were non-linear wave packets, generated by the instability developing at the boundary between the solar wind and Mars. For the first time, observations from two different positions also helped scientists constrain the spatial scale of these structures, and the measurements revealed something important. The ion fluxes inside the observed plasma clouds were 1 to 2 orders of magnitude higher than those measured in typical steady atmospheric escape channels. That means that, during these events, the fluxes could be roughly 10 to 100 times greater than the background escape channels being compared. But there is an important limitation. This does not mean Mars loses 100 times more atmosphere all the time. These intense fluxes were measured inside particular structures during specific events. Scientists still need to understand how frequently these events occur and how much they contribute to atmospheric loss over billions of years. Even so, the discovery changes the picture. Mars does not only lose its atmosphere through a quiet leak. Sometimes, organized structures can carry planetary ions away in powerful bursts. 2 spacecraft helped reveal that connection. And suddenly, the invisible boundary around Mars became easier to imagine. It is not a simple wall between a planet and space. It is a dynamic frontier, a place where plasma streams collide, where electromagnetic forces shape matter, and where, under the right conditions, the edge of a planet's atmosphere can begin to roll like a wave. To understand why atmospheric escape matters, we have to look billions of years into the past. The Mars we see today is cold, dry, and surrounded by a thin atmosphere. But its surface tells a different story. Ancient valley networks suggest that water once flowed across parts of the planet. Lake basins reveal environments that existed long before Mars became the world we know today. Minerals formed in the presence of water provide further evidence that the planet once had very different conditions. Ancient Mars was not necessarily identical to Earth. Scientists are still investigating exactly how warm it was, how much water existed, and how long favorable environments lasted. But the evidence shows that Mars underwent a dramatic transformation. One of the most important changes involved its atmosphere. A thicker atmosphere could have helped create conditions in which liquid water remained stable on the surface. As the atmosphere changed, Mars became increasingly hostile to those environments. But there was no single event that caused the transformation. Mars lost atmospheric material through multiple processes. Some gases became trapped in rocks. Some particles escaped because of chemical and thermal processes. Solar radiation and the solar wind also contributed to atmospheric loss. NASA's MAVEN mission has demonstrated that atmospheric escape is not just an ancient event. It is still happening today, and the young sun may have made the process more intense. Early in its history, the sun was more active than it is today. It produced stronger ultraviolet radiation and a more powerful solar wind. At the same time, Mars no longer had the strong global magnetic field that could have offered greater protection. That combination created a challenging environment for the planet's atmosphere. This is why the discovery of Kelvin Helmholtz waves is so interesting. The new observations do not prove how much atmosphere these waves removed billions of years ago. They reveal a process operating today. Scientists observed that the solar wind can generate large plasma structures capable of carrying planetary ions away from Mars. To understand the ancient impact of this mechanism, researchers will need models showing how frequently these events occurred under stronger solar conditions. But the possibility is compelling. If these waves can help remove atmospheric ions today, what role might similar processes have played when the sun was younger and more active? The answer is not yet known, and that uncertainty is important. The story of Mars was probably written by many processes acting together across immense periods of time. The Kelvin-Helmholtz waves are not the entire story, but they may be another important piece of the puzzle. And somewhere above Mars, that puzzle is still being written. The discovery of Kelvin-Helmholtz waves around Mars may not be only about Mars. The physics involved is universal. Where different regions of plasma move past one another at different speeds, conditions can exist for Kelvin-Helmholtz instabilities to develop. That means similar processes can occur elsewhere in the solar system. Earth also experiences Kelvin-Helmholtz waves, particularly where the solar wind interacts with Earth's magnetic environment. But Earth and Mars are very different. Earth has a powerful global magnetic field. Mars does not. That difference changes how each planet interacts with the solar wind. Mars has become a natural laboratory for studying how a star can influence a vulnerable planetary atmosphere, and that question extends far beyond our solar system. Astronomers have discovered thousands of planets orbiting distant stars. Some may have weak magnetic fields, some may have thin atmospheres. Others may orbit close to active stars, where stellar winds and radiation can be far more intense. Could those environments slowly remove planetary atmospheres? Could the presence or absence of a magnetic field change the fate of a world? Could atmospheric escape help determine whether a planet remains habitable? Mars cannot answer all of those questions, but it provides something extremely valuable. It is close enough for spacecraft to study directly. Scientists can measure particles escaping today. They can observe how the solar wind changes. They can compare conditions at different locations, and they can test theories using real data. The MAVEN and Tianwen-1 observations demonstrate another important lesson. In space science, one viewpoint is sometimes not enough. A plasma cloud detected near Mars tells only part of the story. To understand where it came from, scientists may need measurements from another location. To understand the cause, they may need to observe the incoming solar wind. Together, multiple spacecraft can connect events across an entire system. This allows scientists to see relationships that a single spacecraft might miss. The atmosphere of a planet is not isolated. It is connected to the star it orbits. The sun influences Mars. Mars responds to the solar wind. That interaction changes the flow of plasma around the planet, and some of Mars itself can be carried away. The boundary between a planet and space is not a sharp line. It is an active region where matter and energy are constantly exchanged. Kelvin-Helmholtz waves make that invisible process easier to imagine. Wind over water, a surface becoming unstable, waves beginning to curl. Except these waves are made of plasma, and they can form around an entire planet. Mars is losing its atmosphere right now. The process is slow on a human timescale, but relentless on a planetary one. Particle by particle, the red planet continues to exchange material with the space around it. For decades, scientists have been trying to understand how a world that once contained rivers, lakes, and a thicker atmosphere became the cold, dry planet we see today. The answer is not one catastrophic event. Mars changed through a long and complex history involving atmospheric chemistry, solar radiation, impacts, internal evolution, and escape into space. The Sun became one of the most important forces in that story. Without a strong global magnetic field, Mars was left exposed to the solar wind and radiation from its star. Over immense periods of time, those interactions helped transform the planet. NASA's MAVEN mission has spent years studying that transformation. And now, observations from MAVEN and Tianwen-1 have revealed another remarkable process in action. At the boundary between Mars and the solar wind, differences in plasma motion can create Kelvin-Helmholtz waves. These enormous rolling structures can gather planetary ions into organized plasma clouds and carry them away from the planet. The new observations found that ion fluxes inside these structures could be dramatically higher than those measured in typical steady escape channels. But perhaps the most important lesson is this. Mars is not losing its atmosphere in only one way. Multiple escape processes can operate at the same time. Some losses are relatively steady. Some are influenced by changes in solar activity. Some happen when energetic particles knock atmospheric atoms and molecules into space. And some may occur in organized bursts inside giant plasma waves. Together, these processes can reshape a planet over geological time. The discovery does not solve every mystery about ancient Mars. Scientists still need to determine how frequently Kelvin-Helmholtz events occur and how much they have contributed to the total atmospheric loss across billions of years. But the study gives us something extraordinary, a chance to watch planetary evolution still happening. Every time the solar wind reaches Mars, another interaction begins. Invisible currents flow around the planet, magnetic fields bend, charged particles accelerate, and sometimes the boundary itself begins to roll. Some of that material escapes Mars forever. For us, the change is almost impossible to notice. For a planet, time changes everything. Mars reminds us that habitability is not permanent. A world can change. An atmosphere can thin. Liquid water can disappear from the surface. And the same star that provides energy can also help transform the environment around a planet. That makes Mars more than a story about a lost world. It is a laboratory for understanding planetary evolution. And perhaps one day, it may help us understand the fate of worlds orbiting other stars. So the next time you look at the red planet, remember this: its story is not finished. We are still watching it happen. And if you enjoy exploring the forces that shape planets, stars, and the universe itself, subscribe to PointView and join us for the next journey. Because sometimes the greatest discoveries are not only about distant worlds we can barely imagine. Sometimes they are happening around a planet we have already learned to call our neighbor. Mars is still losing its atmosphere. And now, we may be starting to understand another part of how it happens.